Okay, so as announced over the course forum by email, we're at the tail end of the course, so we've got 2 more lectures, and these lectures are more advanced material and going to be, to an extent, quite technical in nature. I hope I can do the subjects justice. It's a bit tricky getting off the start again in January. Anyway, here we go. So today what we're going to, the topic is something called algorithmic information theory. Which is obviously connected to something called information theory that I'm not going to talk about at all. It's more concentrate on the algorithmic side here. But the basic idea is to be able to talk about the complexity in terms of just the intuitive conception of the word complexity, so how complicated something is, for, say, numbers or words or just finite bits of data, like the bits of data we manipulate and deal with in everyday life. To motivate it, I thought I'd give the following example. So there's a number called a Google. Does anyone know what a Google is? Yeah, 10, so it's 10 to the power of 100. Quite a large number. In fact, Google is the word that Google, the company, took its name from. Only they modified it to make it a sort of nicer word in some ways, and then now it's even become a verb, Google. Anyway, a Google is 10 to the power of 100, and there's a related, even larger number, which is a Google Flex, which is, anyone know? Sorry? 10 to the power. Yeah, so it's 10 to the power of a Google. And these are, well, this one in particular is an absolutely huge number, 10 to the 10 to the 10 to the 2, if you like. But on the other hand, I was able to describe it very succinctly. So these are large numbers. Succinctly means briefly and concisely. These are large numbers. That have succinct descriptions. The idea of algorithmic information theory, or the kind of motivating idea before we get to the algorithmic part, is that we can think about how complicated data is to describe precisely, but to specify. And so, although these are large numbers, they're not that complicated in terms of how we describe them, because we can give them very short and concise descriptions. So this we translate to having succinct descriptions, we translate to, this is low, numbers of low complexity. While plenty of other numbers of this size, so this order of magnitude, so Google many decimal digits, in order to describe them, well, we would be very hard pressed to describe them without listing all the numbers all the digits one by one in sequence. So those would have absolutely enormous descriptions that you probably I always forget how large the universe is, but questionable whether one could fit a description of an arbitrary such number into the universe, into the physical universe. So what's this got to do with computability or algorithms? Well, the point is that having measured an algorithm, having models of computability like we have in this course, give us a means of saying, how do we describe a number, or how do we describe a string? Well, we can describe it by, say, a Turing machine. And yes, one can produce a quite small Turing machine that will produce Google as its output. You have to wait a very long time to see the output, but never mind, it will eventually produce Google as its output. So we can measure the complexity of, say, words in terms of the size of the Turing machine that's needed to describe the word. And that idea is due to Kolmogorov, same Kolmogorov that basically invented the modern formulation of probability theory. Kolmogorov line the intuitive idea, the complexity of a word W, and just to have a convenient fixed alphabet, we'll just consider bit sequences, so we'll always have the alphabet of binary sequences. We're now talking about finite words as opposed to the last three lectures that were about infinite words. As essentially, this is still an informal definition, but as the size of a Turing machine of the smallest Turing machine smallest Turing machine that doesn't take any input. This is an informal idea because we'll make it precise in a kind of slightly more mathematically satisfactory way. So, it's an informal idea. Equivalently, this view is going to be useful. So equivalently, rather than considering the size of the Turing machine, well, instead of using arbitrary Turing machines, we could just use one Turing machine, the universal Turing machine, and think of the size of the input we need to give the universal Turing machine in order to get the output, the word W. Because the input to the universal Turing machine is an encoding of the Turing machine that we're simulating, and basically considering the size of that is pretty much the same thing as considering the size of the Turing machine. Equivalently, as the length of the input string, the shortest input string that we can give to the universal Turing machine, UTM, to get W as an output string. So we're going to give a mathematical definition based on this. The But at this point in the course, we don't want to go back to Turing machines. And in fact, we can do this in a way that's more mathematically satisfactory, still fundamentally using the universal Turing machine or something equivalent. I mean, I'll just show you in a moment when I move the camera how we're going to do that. So, rather than universal machines, we can talk about universal partial computable function. Computable partial function. And because everything is going to be, this lecture is going to be about binary sequences, binary words, I'm going to go back to, so it's like sort of rewinding the course way back to the beginning. We're going to go back to considering functions as functions on words, so like we did when we were considering Turing machines. So we're going to consider partial computable functions whose main set of binary words, and codomain is also a set of binary words. Binary word as input, and potentially return a binary word as output. And if such a computable partial function is meant to be universal, this is definition of universal partial function, if it simulates any other computable partial function in the following way. So if for any computable partial function B, so partial function on Earth, there exists some word that codes the universal partial function V. Not the universal partial function. And I don't want to call this V, I want to call this F. So for any computable partial function F, there exists some word V that encodes F in the following way. So there exists a word, binary word, which I'll call V sub F. Might be, in general, there exist very many of them, but it must exist at least one. But that's binary word, such that we can compute F using the universal Turing machine on strings prefixed on finite words prefixed by VF. So in other words, we can compute F, so it's such that for all input words W, we can compute F of W by using the universal function applied to the word. We give VF, so we view this VF as encoding the function F, and we simply concatenate that with the word W afterwards. So it's a concatenation of these two words. Okay. Right, so I haven't asked this kind of question for a long time, but just to check that we're awake, I've made one deliberate mistake on this. Sorry? The clean equal, because of course these are partial functions, so they may not be defined. Yeah. it's quite nice this, because whereas saying what the universal Turing machine is took several sentences or quite a bit of definition of what it does. Yeah, this has a very concise definition. It's a bit like the universal partial function on the natural numbers as well. That's what it's a concise description. But here we're using the operation of concatenation. And a proposition that I'm not going to prove is a universal function exists. Universal computable partial function exists. Partial function exists. So we're not going to write out a proof of this, but how do we show it? Well, basically, this is going to be the universal Turing machine, the function computed by a universal Turing machine. The only thing is when we did our universal Turing machine, we gave ourselves quite a large alphabet so we can do things nicely. Here we've only got binary words, but of course we can code things up using binary words. The other thing we did with our Turing machine, the universal Turing machine, was we separated the description of the description of the Turing machine that computes the function f, which is this part, from the input string being given to that using a bullet or something. I don't quite remember what symbol. Yeah, I think it was a bullet. So we use a separator symbol. Here I'm just concatenating the strings, but you can get the universal Turing machine to work in that way, and you can think about it. So we have a universal function. And now, so we're going to, now we can give a mathematical definition of Kolmogorov complexity using this idea. So it's the length of the shortest input string that we can give to the universal Turing machine that gives the word that we classify the complexity of as output. So we can do that using the universal function f. So given a universal function, universal function u. So given a universal function u, the Kolmogorov complexity is this called, or this sometimes descriptive complexity, Kolmogorov complexity, written C, capital C W, C complexity of a word W, so binary word is, so it's simply C of W, simply the minimum over all. Just going to look at the notes to see what letter I use, which doesn't really matter, of course. It's simply V, the shortest length of string V, such that U of V is W. The shortest length of the shortest input we can give to the universal function, so that we get W back. Of course, every finite word W, for every finite word W, this is defined, because for every finite word we have there is some input we can give the universal machine to get that word back, namely some description, some program that computes it, but basically it's just a case-by-case statement that contains every symbol of the word in print this, then print that, then and so on. So NV, every word is signs a finite number. So of course this is dependent on the machine, sorry, not the machine, on the universal function u, so we'll write C sub u to be a bit more precise. But because it's dependent on our choice of universal function, it might not look very canonical. There are many different universal functions and they might give extremely different answers. On the other hand, it turns out that, here it is, turns out that it's actually well defined, or canonically defined in a nice sense. So suppose we have two different machines, how do the complexities of how do the two different we have two different universal machines, how do the two different complexities we have of the same string W how do they compare to each other? The proposition, suppose U prime are universal beautiful functions. It's W. If we consider the complexity of W with respect to U prime, how does it relate to the complexity of W with respect to U? Can anyone see this? Just, I mean, obviously some of you might be looking at the notes, in which case. There's a very nice fact here, which is that there always exists a constant C such that for all words W, U prime complexity of W is less than or equal to the U complexity W plus C. So there's only an additive constant that separates them. And of course, in the other direction, because U and U prime is arbitrary which one we call U and U prime, we have the same thing in the other direction. So one way of, the standard way of writing this is that the complexity, the U complexity of W and the U prime complexity W, they differ by an additive constant, so we write that this is one equals the other plus a constant. Okay. So it's more standard notation. So this is proved in detail in the notes. It's a very short proof. I don't want to give the detailed proof here because it takes time to write things on the board, but the idea is simply this, that we've got two different universal functions. Well, so let's work with the universal function U and then consider the universal function U prime. Well, the U prime is a computable function, so it has there's a finite word V sub U prime that represents that computable function. And then we simply can convert any computation involving the universal computable function U prime to a computation involving the universal function U by prefixing it by the prefix V sub U prime. And that prefix is our additive constant that fits into this inequality. It works the other way for the other. It works the other way or the other direction. Okay. So next we're going to consider just wondering what order the So we've got the definitions now. So because of this proposition here, the actual Kolmogorov complexity of one individual's word is very dependent on the underlying universal function. It can differ wildly between them. But if we prove properties of complexity that hold for all words, then once we start talking about such properties, then the choice of universal function is not important because we only have this additive constant that differentiates between the two complexities. So I started off with the example of Google. Obviously, one doesn't normally write that over the binary alphabet, but it doesn't really matter. You can imagine, so Google, and Googleplex as binary words. There's going to be some very short program or Turing machine that describes those. That's going to translate to a short input to the universal function, and it's going to turn out that short input so that short input gives us a short length, minimum length for the, so it gives us a low complexity. So those are going to be words that have low complexity. But we can prove that there necessarily exist words that have high complexity. So what would a word of high complexity mean? What do you think? Sorry? Well, pi is not a finite word. So it doesn't even fit into the. So we're talking about finite words here. So, but actually, so sorry, but while we're on the subject of pi, any prefix of pi will have low complexity because we have, I mean, okay, the formula is not as simple as that for the Google, but we have reasonably straightforward algorithms that compute the digits of pi. And so such an algorithm is giving us a small word, and the digits of pi are going to have a pretty low. So the prefixes of pi are going to have pretty low complexity.
Some word that has a complexity in the order of its length.
Right, exactly. So kind of the worst thing we can have to describe a word, you hope for some succinct description, but in the worst case, you can always resort to taking the characters one by one and writing the program that basically lists the characters one by one and outputs those. So you can never really do worse than a generating word V that essentially contains the characters one by one and also contains enough padding around it to get the program to work to help put those characters in the right sequence. And that can actually be reduced to a constant amount of additional baggage on top of the finite words. So word is going to have high complexity if its complexity is the length of word, again, plus an additive constant, if you like. And exactly what that additive constant is kind of up to you to choose. But what we can prove is there always exist, in a sense, words of high complexity. In the following sense, for any n greater than or equal to naught, exists a word W of length n such that complexity of W is equal or it's greater than or equal to n. Okay. There always exists at least one word whose complexity is, we're now forgetting about the additive constant, but whose complexity is at least n. Can anyone see a proof of this? It's very simple. I mean, not simple to see, but the proof, once you've seen it, it's very simple. But so we're considering words that can be described. So notice every finite word, if you like, we can view V as a sort of, we've got a kind of dictionary of words, and we're using given by U, and V we can view as key to getting the word W. So every, and if we consider all possible keys V of length strictly less than n, well, how many are there? Well, there's 1 of length 0, 2 of length 1, 4 of length 2, and so on. But the words, the number of keys V of length strictly less than n is 2 to the power of n minus 1. And so some of those will even result in, some of those might result in divergence for the universal function. Some others might duplicate words that we might get duplicates. But even if everyone were defined and gave us a different word, we would only be using up 2 to the n minus 1 words of length n, and there are 2 to the n of them, so 1 would be left over, and that word necessarily has complexity at least n. Okay? So I'm not going to write the proof in detail, but proof are only at most 2 to the n minus 1, 2 to the n minus 1. That words with complexity strictly less than n, because there are only that many different keys V available. So since there are 2 to the n words like that, at least one plus this picture is quite theoretical, of course, because we're talking about theoretical models of computation, like Turing machines, and then the universal function derived from that, and this kind of definition of complexity, but still relates to things in the real world. And then one of the things that it relates to is the notion of compressibility, in terms of data compression. If you think about data compression, which is obviously a very practical thing in computer science, the point of data compression is you have a big data file, which is like a very long word, and we want to use up less, we want a smaller file that we can recover the original from. So we're looking for some sort of small key from which we have a computable function that will give us back the longer piece of data. So relating to that, Kolmogorov came up with the idea that so although when one's looking at finite words, there's always this additive constant involved in the depth. So it's hard to say anything absolute about an individual finite word, because you could change the model of you could change the universal function, and engineer for that individual finite word. You could engineer sort of practically anything, so you could make its complexity as low as possible. But Kolmogorov considered the idea that if you look at infinite words, then, so if you're thinking of data streams now, the infinite word is like a data stream. Kolmogorov thought that one might be able to describe the property of a data stream being essentially unpredictable, in the sense that we cannot compress, for any prefix in the data stream, we can't compress it to something smaller. So somehow this was kind of idea of modeling a completely unpredictable data stream. You can't predict any information about what's going to suddenly say, oh, you can't predict anything about what's going to come. So we can define that using the notions we have. So we say an infinite word so we'll use P again for infinite words, like we've been doing in the last few lectures. So this is in here 1 to the omega, is incompressible in the sense of Kolmogorov. So I'll just write K incompressible then. If for all n, well, let's write it precisely. So if for all n, we're going to have this prefix lengths, we look at the complexity of prefix of length n of the word P. This is going to be at least n, potentially minus some additive constant. So you've got some, we're allowed to lose a few bits of data, we're allowed to compress it something a little bit smaller, but we've got some single constant that is a bound on how far we can compress the prefixes. So to say this, so this is the shorthand. To say this precisely is if there exists some finite constant C, such that for all n, the complexity of the prefix P, the n symbol prefix of P is at least n minus C. Okay. So it's a nice notion that is using Kolmogorov complexity to describe and our first sort of main results. First of one of the results today is going to be the following proposition. Theorem, actually. Which is a bit of an anticlimactic theorem because it says this is a bad definition. So, and it's a nice theorem because the proof is illuminating and it leads us on to consider a different, more subtle notion of complexity, which has better properties in some ways than the Kolmogorov complexity. It's closely related. The theorem, which was proved by Martin Löf, who is the same Martin Löf that came up with Martin Löf's type theory. So this was something completely different he did before he did type theory. So there's no infinite sequence is Kolmogorov compressible. Oh, looks like a nice definition. Not a useful definition. It's 3 o'clock, so let's. Are there any questions?
Constant and sequence zeros is nice.
Well, so that's very non-compressible because so we're asking the constant infinite sequence of zeros. If we take the prefix of length Google, so the first 10 to the 100 zeros, for it to be incompressible, then it would need to have complexity close to a Google, but we can describe the first Google, the sequence of first Google zeros, the sequence of Google then zeros very concisely by the program that says computer Google, which has a short description, and then repeat Google many times, output a 0. So it has very low complexity. So that's very compressible. And basically, the longer the program that outputs the complexity of the prefixes of such a constant sequence are going to go up at the order of log of n, because we need to say how long the prefix is as part of the input. But that grows obviously much less slowly than n.
Theorem is probably incompressible.
Oh, it is, yes. I think I'm sorry, yes. Thank you. Yeah, good. I'm sorry, Karen. Yeah, okay. Yeah, good. Many sequences are compressible. In fact, all sequences are compressible if one takes the compressible to be not incompressible. Okay, so it's basically 3 o'clock, so we'll start again at basically 1:15. So the notes contain a detailed proof of this. I'm going to give an outline proof in the lecture. Also, the currently published notes, the detailed proof of the currently published notes, the function h I defined seems to change name to g in the middle of the proof. But obviously I shall correct that afterwards. I shall call it h in the lecture. So to prove this, proof if you like, but you don't need to write that. We're first going to do something very simple, which is just look at an encoding of binary sequences as numbers. Of course, we already have an encoding of sequences as numbers, but the natural encoding of binary sequences, we have an encoding of natural number sequences as numbers, but I want a bijective encoding of binary sequences, and there's a very simple one. So we're going to define, and I'm going to use the same corner quotes for the encoding. So this is the encoding of binary sequences of numbers. So the encoding of a word, binary word W, is well, the formula I like is this one, where essentially we consider the word W as a binary number in the reverse order, just so the indices are easier to deal with. So we count up to the length of W minus 1, and we every digit Wi multiply by 2 to the minus I. But actually, we really consider the binary number that we get by reading W followed by 1 in reverse, just to make sure that we don't collapse things by having leading zeros. So we're going to add to that 2 the minus length of W, and now it's a bijection onto positive natural numbers. So to make it bijection onto natural numbers, we subtract 1. Okay, and this has an inverse that is not easy to define in a closed form like this, but it's an easy algorithm to compute it. So I'll just write, so I call this inverse word. And this goes obviously from n to 0, 1, 5. Okay. And using this, I'm going to outline proof.
Should those powers be made?
They are 2 to the minus. Yeah. That's sorry, you don't know me. Yeah, sure. Of course. I'm still too stuck in the real number part. So we're often using negative. Yes. I wonder if they're positive in the notes. Well, they are positive in the notes, which I wrote earlier today. So, good. Well, I'm glad somebody's awake. Right. So now I'm going to explain how we get we fail to get the incompressibility by. So now we're going to go to proof, and I want to show for an arbitrary p, an arbitrary infinite sequence p, how we can compress it by any number of bits. So for any number of bits, we'll find some prefix for any number of bits, d say, we'll find some prefix length n, such that we can compress the first n symbols of p by at least d. We can do that for any d, so we're now going to have a fixed constant c, so that we can always satisfy this inequality. Right, so now we're going to prove. So let P be an infinite sequence, so that's arbitrary. And we want to compress by some number d. So we want to find some prefix of P that we can compress by d bits. So consider any d greater than or equal to 0. And we want to compress by d bits. So what we do is we consider sequence P0, this is our sequence P1, P, all the way up to P, D minus 1. So this is the first D bits. And these are the D bits that we're going to extract without, we're going to recover without knowing them. We're going to lose these bits when we compress. So here we've got D bits. But what we do is we look at this and we apply our numerical encoding to it to get a number. And then what we look at next is the next, that whatever number we get out, let's call it, well, we'll just call it this, the encoding of this. So we look now, we've got here PD, PD plus 1, and so on. We're going to look at the prefix as far as the next. So here we have the number we get from P restricted to D. Okay. We look at that many bits. So here we get to P, D plus the number from P restricted to D minus 1. Again, to get that many bits. And the thing is, we can actually recover these D bits just from this information using the function h, which I'm going to define now. To define h, which is a function binary words total by h of w. So this is the function h that changes name to g in the middle of the current latex proofs, but anyway, it's going to be called h. Now h of w simply, when applied to w, it simply computes the simply takes finds the length of w, computes the word that we get back from whose encoding is the length of w, and then follows it by w. So here we've got a concatenation of, so it's simply concatenating two strings that can be computed from w. And we notice that this sequence here that this sequence, which is our infinite sequence P restricted to D plus, that's the first D plus the word in word that P, that the first D bits of, sorry, yeah, plus the number that this word encodes, that many bits. So this is, by the way we've defined it, this is H. H applied to this part. So H of P of the word that goes from PD to P of D plus P restricted to D minus 1. Okay. And because we're applying function h to it, we can use the universal function together with the code for h and this information. So this is u of the h of followed by all these. Okay. So the Kolmogorov complexity of this, which is the whole word we've got here, is basically just a constant away from the Kolmogorov complexity of this word. And because this VH is the same for, is independent of the number D we started with, this is just a single constant. And so we're essentially modulo that constant. We're compressing the word. We're compressing this word by losing D many bits. Okay. So that's the idea for the proof, and the full details you can find in the lecture notes without the ideas so much. But there's another way of looking at this idea, which is so essentially what we're doing here in order to recover the whole prefix from just a portion of it where we lose D many bits is we're exploiting the following fact. When we give an input to a computable function, an input word to a computable function, we're giving some information to that function that we're using to calculate the result. And that information consists of the bits that we're giving it in the input. But in a sense, we get some additional information as well, which is the length of that input string. And that length of the input string gives us potentially an extra, essentially log2 of the length, many bits of information. And that's this D is exactly, well, log2 of this number plus what, the floor of the log2 of this number plus 1. So it's basically this D is log2 of that from the way we've encoded it. And we're exploiting this fact that a computable function potentially exploits more information than just those given by the bits in a word, because we also see what the length of the word is, and that gives us an additional number of bits of information. And so with those bits, we can vary the length of that amount of information if we want to find a prefix that we can compress, by that many bits. So a lot of people were, when this was first noticed, were thinking, well, what's, the notion of incompressibility looks like a nice notion that should make sense, but there's this problematic aspect here that essentially something's wrong, because when we measure the complexity, you'd like to measure the complexity of a finite word W in such a way that so ordinary information theory is about measuring how many bits of information you have in some piece of data. So we'd like to know how many bits of information do we need to be able to define something. But Kolmogorov complexity is not really saying that, because it's measuring the length of an input, but the length of an input doesn't just contain that many bits. An input of that length doesn't just contain that many bits, but we also get the additional information of the length of the input there, which is giving us some extra bits that we're not taking account of in the complexity. So Chaitin was one of the people that saw a way of addressing this. Various different solutions have been proposed, but it is the one that has become most popular. So Chaitin proposed a variant notion of complexity called prefix-free complexity that addresses this problem. Due to Chaitin. So the idea of this is as follows. So if you're giving some input to a computer, like you've got a computer program, and you you need to give it some input via the standard input. You type in your string, but you don't just type in your string, you also press return at the end in order to say I have finished my input. So doing that, you are actually giving more information than just the characters itself. You're giving the characters plus a termination symbol. So in a sense, inputs to a computer program satisfy the property, a particular property that they're kind of self-delimiting, because you use the enter to say I have completed the input. The Chaitin said, well, why don't we measure complexity in a similar way, that we consider functions that take their input words but treat them in a self-delimiting way. And when you look at if given so we can't get the length of it out. You can kind of imagine the bits of the input being given one by one, and only at a certain point you'll get the full input, at which point the computable function will detect that that's the full input and will then give you the result. And one way of saying that mathematically is we want the domain of the computable partial function to be what's called prefix-free. Because, so prefix-free means if something is in the domain, so if the computable partial function halts on that word, then no proper prefix of it can be in the domain, because in a sense, we haven't yet got the information that we've completed the input at that point. And also no proper extension of it can be in the domain, because once we've got the word that's in the domain, that word contains within it the information that we've finished the input, and so we don't want to consider any longer sequence would be inadmissible because we've already finished the input. So he's modeling this situation by a function, a partial function f from infinite words to infinite words is prefix-free if domain of f is of course a subset of finite strings, satisfies all pairs of words with the domain of f. It's not the case that w is the proper prefix of w prime, and it's not the case that w prime is the proper prefix of w. But it's enough to say it once, because so w is not a proper prefix of w prime. We can also talk about the set of words being prefix-free. So then, a function that's prefix-free has this self-delimiting property in the sense that when you have an input string that's in the domain, so nothing shorter than that could have got you there, so it's kind of completed itself in saying it's in the domain, and also no extension of it can be in the domain either. And so again, we have a universal prefix-free function. Prefix-free function u from words It's universal. If the same property holds as before, so this is going to be computable. If for any computable partial function f, we have to set there exists code word for the word for f. Such that, but just as before, f of w, such that for all w, f of w is clearly equal to u of df by w. So actually, when I say computable function here, it's actually computable prefix-free function. And you can check for yourself that if u is a prefix-free function, then it automatically holds that if you fix any finite prefix of inputs and consider the function f that's induced by this equality, you get back a prefix-free function. Okay? That follows from the original function being prefix-free. So this makes it's a nice self-consistent definition there. And the prefix-free complexity word w is called k of w is simply the same as before. The minimum length of the v such that u of v equal to w. Or where u is a universal prefix-free function. Okay, so it's just the same definition as before, but we've enforced by this notion of prefix-free, we've enforced in it the property that we're not allowing v needs to all the information contained in v is contained in the bits itself, because the bits of v itself determine the length. We're not giving the length as additional information. V already determined. I mean, in the sense that no prefix, no shorter string and no longer string could have been in the domain. So in the notes now, I mean, I used to do it the opposite way around, but I'm using the standard terminology, which is the standard notation. So I find it a bit weird because Kolmogorov introduced Kolmogorov complexity, and that's then given the symbol C, and Chaitin introduced Kolmogorov complexity, and that's given the symbol K. Of course, the symbol C in Kolmogorov complexity stands for complexity, but I don't know why prefix-free complexity has that. Anyway, you know, it's maybe we can think of it as kind of mutual respect between Kolmogorov and Chaitin or something. The two definitions use the other one's initials. Right, so this is prefix-free complexity, and it has similar properties before. So once again, it's well defined, so this is again dependent on the universal prefix-free function. But for any two different universal functions, it's defined, it's equal up to a negative constant. So once again, it's as canonical as the notion of complexity we had before. And again, by the same argument, no, wait a minute, what do I want to say? Oh, I missed out an important fact about Kolmogorov complexity, because now I want to do the analog for the prefix-free complexity. So let me just finish the sentence that I interrupted earlier. So by the same argument, we do have, of course, the same argument gives us for any n, there exists a W such there exists a W length n such that prefix-free complexity is at least n. The same argument as before for that. And the thing that I forgot to talk about, which is actually quite important, is upper bounds on complexity. So for Kolmogorov complexity, there's have the upper bound, which is for any W, for any W, the complexity of W is always at most the length of W plus some constant. Okay, say why in a moment, but the official statement for that is that there exists a C that works for all words. There exists C such that for any W, C of W is less than or equal to the length of W plus the constant. This is capital C complexity less than. So this is an important contrast to there exists a word of high complexity of length W, which is what we had earlier. But moreover, that is modulo a constant, that is as high a complexity as you can get. And the reason for that is because for any word, I mean, I did say it, I just didn't write it in this form. For any word, we can basically write a program that contains within it the list of the sequence of characters in the word, and there's just a constant amount of additional stuff that's needed to get to make the program itself. Like if one was writing it as a computer program, it might be print to standard output or something like that. That kind of stuff, and the for loop that you need to go through, and this kind of thing. That's not really a for loop because everything's this, and it's a sequence of commands in this case. Okay, so we have the upper bound with and it's just the length of W plus O1. So one thing where prefix-free complexity gets more complicated is the upper bound is not so straightforward at all in this case. So Now, I'm going to, in the lecture, just be satisfied with a very simple upper bound. But if you read textbooks on prefix-free complexity, there's a few pages of work on establishing the best possible upper bounds for prefix-free complexity. But the one that we're going to do is so prefix-free complexity upper bounds. Crude upper bound. Just the following. Just for any d greater than 1, there exists the such that the prefix-free complexity of a word is bounded above by d times the length of w plus c. The idea is we make d as close to 1 as possible, so we can put in any constant multiplier that's strictly greater than 1 here, and we can we're always below that multiple of the length of w by a constant. But we can't get d down to 1 itself if we've got in the case of Kolmogorov complexity, you can make d 1 itself. Okay, so I'd like to, again, the notes have a detailed proof of this. I'd like to give an outline proof in the lecture just to give you an idea of why this works. The only thing is I haven't actually prepared the outline, so I do have the detailed version, but should be all right. So the outline proof, I'm not even going to involve d in it. I'm just going to give the general idea, which is for any large n, we're going to, well, it doesn't even need to be large, but we can make it large, and the smaller d gets, the larger n needs to get. And for any large n, we work with encoding of words over the binary alphabet as words over a different alphabet with where sigma has 2 to the n minus 1 symbols in it. Okay? And the point is we can then let me call so let's again use the corner brackets for the encoding. So this takes a word in the binary alphabet to a word in the alphabet over sigma. And the point then is that we can work with. So what we want to do is we want to encode a binary word into a word that is self-delimiting, so we can work with it in a prefix-free way. And we then map a word W to the input to a universal prefix-free machine. We encode the word W using the alphabet, using this alphabet with 2 to the n minus 1 symbols. We then re-encode the alphabet using 2 to the n minus 1 symbols, by encoding every symbol here as a binary word of length n. Okay, so we have a mapping. So let's write double corner quotes, but it's a different operation. Let's use angle brackets or something. But here we've got 2 to the n minus 1 symbols. So if we use binary words of length n for each symbol, we've got 2 to the n of those, so we can choose one of them for each symbol in sigma. And the point is, there's one symbol, there's one binary word of length 2 to the n that we haven't used, and that's because we've only got 2 to the n minus 1 many symbols. So let's suppose that's 0, 0, 0 n times. We add that at the end, and this is we use this is like our enter. So we're inputting this input, and then we press the enter key. And because we get 0 and n times, we know that we're not encoding something input. So we use this alphabet so that we can use sequences of length n, that we can use words of length n to encode the symbols of this alphabet, and give us room to have an extra symbol that we're going to use as the termination symbol. And if we do this in a nice way, for large enough words, the length of this word is basically the length of, it can be pretty much the length of the original word plus n many symbols. And we can, if we make n large enough, we can eventually get that below d times between d times the length of the input by w for any by w. So I didn't want to go through it in detail, but I hope you've got some idea about how the proof works from that sketch. Maybe it would have been clearer to work with some specific examples of these things. Generally, are there any questions on that? Right. So now that we've done this, we've got a different, little bit more subtle, but trying to motivate the reason for this prefix-free requirement. And we can basically make the same definition of incompressibility again, but now with prefix-free. We say an infinite word, the infinite words is prefix-free, incompressible. And it's exactly the same definition as before, but with k in place of c. So here, this is a c. Such that all n prefix-free complexity of the first n of the n-length prefix of p is at least n minus c. And now, I won't write it as a theorem at this point, but the theorem is going to be that such a prefix-free incompressible sequence exists. Maybe that in itself is not super exciting. It means it's not a pointless definition, at least. But what's more interesting is what the prefix-free incompressible sequence is. And what we're going to, so the last part, what we're going to do in the last part, we're going to show that something called the halting probability, very famous constant in mathematics, well, in certain parts of mathematics, but Chaitin's halting probability, omega, capital omega, is prefix-free incompressible. Last bit of the lecture is going to be what is Chaitin's halting probability and why it's prefix-free incompressible. Okay, yeah, it's basically 4 o'clock, so we'll start again at 1:15. Any questions? Okay, so it's break time. All right, so this part's going to be about Chaitin's halting probability. And the idea is this: we've got our universal prefix-free, so it's again going to be dependent on our choice of universal prefix-free function, but whichever universal prefix-free function you choose, the halting probability is going to have the same crucial properties, for example, being incompressible. And why it's called the halting probability is this, so the idea is omega is the probability that the universal function halts is defined, U halts, if given an input generated randomly by tossing coins. So how do we do that? We toss a coin to get the first bit, we toss a coin to get the second bit, we toss a coin to get the third bit, and we keep on tossing a coin until, if ever, we get the finite sequence that we've generated, we get one of these words that says that they're self-delimiting, that's the point of the prefix-free thing. You get a word that says, yes, I am a completed input, namely I am in the domain of the universal machine, and in which case, at that point, we halt. But yeah, if we're lucky tossing the coins, we shall get to such a word that is in the domain of the universal machine, and if we're unlucky, we won't. So in other words, omega, this pen's not very good. So omega is the sum over all words W in the domain of the universal function. And for any word, so this is like well, for any word, we got it by tossing a coin, length of W many times. So the probability of us getting that word was, now we do need the minus, 2 to the minus the length of W, right? So that, it's some of these for all words in the domain. And this is indeed a well-defined probability. It's a number less than 1 because the domain is prefix-free. So if you've got 2 different words that are in the domain, then neither one is the prefix of the other, which means the cylinder sets of those 2 words, their intersection is empty. And because of that, this indeed does calculate so this sum corresponds to a disjoint union of cylinder sets. The probabilities of a disjoint, the probability of a disjoint union of cylinder sets. Okay, I'm just curious, has anybody heard of Chaitin's halting? I mean, it's a reasonably famous constant that you might have. Yeah, so he wrote a book about it. Or
no, there is he researched on it, I think.
oh, okay, right. So
I didn't read it, but
okay, so people like this number, and its properties. So because it's incompressible, as we'll see, it's actually very hard to. So obviously, it depends on a particular model of computation and a particular, which means a particular choice of prefix-free function. But people have their favourite choices of prefix-free functions, and I think there's a team in Australia that have been engaged in trying to calculate the bits of omega. Oh, the bits. Well, there's just a number here, but then P of omega, as I'm going to call it, which is an infinite sequence of zeros and ones. So this is just going to be the binary representation of omega. So the binary digit is 0 point P, 0 binary point P, is the unique number that gives us back omega, and it's unique because it's a rational number. It's an irrational number. So if it were rational, it would be quite easy to predict the sequences. Anyway, there's a team in Australia that I think have calculated the bits of omega for their preferred model of computation about as far as 13 bits or something like that. But that's not, it's the strange things people like to do. But what's astonishing about this number is it contains a lot of information in it. So, for example, there are things like that if we knew this number to so many bits, and it's not very many, then we would be able to computably determine from that in a decidable way whether or not the Riemann hypothesis has a proof in ZFC of less than a certain rather enormous size or something like that. I don't remember exactly, but you can get that from not knowing too many bits of omega, you can get that sort of information out of it. So conversely, you can imagine it's very hard to get to determine what the bits of omega are. And if we know omega, we can also solve the Turing halting problem as well. So, which is not. There's a nice proof of that, but that would take us too far afield for today. What I want to do today is show that that theorem sequence P omega is prefix-free incompressible. Roughly speaking, this says if we want to know a prefix of length n of omega, we basically need to know all the bits. We can't modulo some finite constant or something like that. I mean, we can't. There's no way of getting the bits from less information than the bits itself. No way of making the information manageable. Anyway, the more I try to explain it, the less clear it gets. So let's stop at this point. Okay, so I want to end with a technical proof, and then that's going to be it. Yeah, so maybe just right here from this, because P is the binary representation of omega, it's going to be useful to have this, so we can write omega as the sum of just what we get from extracting the number from the binary representation. So we take the ith bit and multiply it by its weight, which is 2 to the minus I plus 1. Okay. Okay, so the basic difficult thing is going to be the following. So we shall define a computable function partial function on words, on binary words, with the following property. So satisfying that for any n greater than or equal to 0, f is defined on the prefix of omega of length n. That's defined, and the prefix-free complexity of f applied to that prefix. So f applied to that prefix is defined, so it gives us back some word, and the Kolmogorov, the prefix-free complexity of that is strictly greater than the number n. Okay, so we've got a function that any prefix gives us back a word whose, for any prefix of omega gives us back a word whose prefix-free complexity is strictly greater than the length of the length of the prefix. So constructing this function is the tricky part, but once we've got that, there's a quite easy end to the proof. So I'm going to do the end to the proof first. So if you've got this property, then so from this property, there exists a C such that for all n greater than or equal to 0, the prefix-free complexity of f of p of the n character prefix of omega, the prefix of length n of omega, is less than or equal to prefix of the prefix itself, the complexity of the prefix itself plus a constant. So why does this hold? Well, in the lecture notes, this is a lemma, but it's very easy to understand this lemma. And the lemma is whenever you have a computable function on words, the prefix-free complexity, it can only increase the prefix-free complexity of the input word by a constant at most. Because when you've got a computable function, you can use that computable function if you've got any description of an input word, you can simply use the description of the computable function itself together with a description of the input word to give you a description of the output word. So whenever you have a computable function, it at most increases. This has got nothing to do with that we're giving the function f here a prefix of the halting probability. It's just we've got a computable function, so there's necessarily a constant that it can increase, that it can at worst increase the prefix-free complexity by. And once we've done that, we simply put this together with that, and so by the two highlighted inequalities, by the orange inequalities, we have that this is greater than equal to this plus c is greater than equal to that, and that's greater than n. So k of p restricted to n is greater than equal, that's greater, so that's greater than n minus c. Okay. So we've done even better than our desired inequality to strict greater than. But I mean, it's just a matter because obviously c could be one different from how it is. Okay. So the remaining thing is to define f and to prove that it works. Works as follows. Yeah, let's move the camera. So that W0, W1 be a computable enumeration of the domain of U without repetitions. Oops. So the U, this is the universal computable prefix-free function. The U is a computable partial function. Its domain is clearly infinite because it's a universal function and you can give it inputs to compute every possible output sequence. Its domain is input, so its domain, and it's a computable partial function, so its domain is a computably enumerable set or semi-decidable set. We're now talking about sets of words, but anyway, you know what a semi-decidable set is. In the lecture on computably enumerable sets, maybe we did or maybe we didn't have the fact that any infinite computably enumerable set can be given an enumeration, a computable enumeration without repetitions. I'm not sure whether or not I included the fact without repetitions in that lecture, but if not, it's an easy exercise to prove that it can be, you can find a computable enumeration without repetition. Because of that, we have this. And now what the algorithm does is, so the algorithm, so given an input word of length n, so let's call that W0 up to Wn minus 1. And here, now we're defining the general algorithm F, so we're not assuming that this word, I mean, it could be a prefix of the halting probability, but it doesn't need to be at this point. It's just an arbitrary input word. The algorithm finds smallest capital N, so little n is the length of the input word, finds the smallest capital N greater than or equal to 0 such that
Two variables. W, I,
have we?
yeah,
Oh, yes. Thank you. This is P0. Let's call this P0 up to P n minus 1, which is what I got in the notes. But importantly, this is an arbitrary little P, is not necessarily, it need not be P of only. Yes, thanks. I'm just so used to calling the general finite word W. Anyway, what we do is we find the smallest n such that if we sum the weights that we get, the probabilities of generating with our coin tosses, the probability of generating the word WI in the domain of the universal function. If we sum all those probabilities up to we sum the first n of those probabilities, then we get something larger than the binary number represented by P. So 2 to the minus I plus 1. So this is the binary number represented by P if we read it backwards. Okay. Of course, this need not exist because this is always going to be smaller than omega, because omega is the sum of these things up to infinity. It's always going to be smaller than omega, and this could be this could be these could all be 1, for example, in which case this would not hold. But we say is the smallest such n if such an n exists. And we can define such a smallest thing because this is decidable, this property, for each fixed n, it's decidable, and so we just count up through the n's until we find one, if we ever get to such one that satisfies this. And then the algorithm or F returns the first word V, that's a word over the binary alphabet, where this is the first binary word in our enumeration of binary words, which we defined earlier using the word function, which was the inverse to the encoding of binary sequences I gave. So it's the first such V in the enumeration of binary words, such that V is not contained in the set U of W0 all the way up to U of W capital N minus 1. The point is we found a capital N such that the probabilities of all the cylinder sets of those parts of the domain of the universal function take us above the probability represented by our input word. And if we've got such a thing, we then we look at these words that we know are in the domain of the universal function. We look at the words that they have given us or that they define for us via the universal function, and we find a new word v that's not represented so far by so we've got here the universal partial function gives us these capital N many words, which there might be some duplications, although actually by the construction of the argument there can't be duplications, but anyway, never mind. We take the first finite word that's not contained in that list. And that's it. This is so this B is F applied to P0 up to Pn to that word. Okay. And what we need to show is that this function f satisfies these two properties. That f is defined on any prefix of omega and this property here. So to show firstly that f is defined on the prefix of omega of length m, so now we'll work with P omega of length n. So I'm just going to write P0. I don't want to write omega all the time, so I'm just going to write P0 to Pn minus 1 for this. So we have n indeed exists because well, if we look at what happens if we sum the first little n minus 1, so here we're looking at the contributions to the probability capital omega of the first n elements of the sequence P supremum omega. And this, because, so this is the contributions, sorry, I'm off the camera, but maybe let's correct the camera. Right, so we've got these two formulas for omega. So this is, so we've got something below omega that's given to us by the approximation to omega that we've got so far, by the n element prefix here, but also omega was expressed as this sum of probabilities of the domain generated by the domain of the universal function. So eventually, if we cut this off at a little n, eventually this sum here is going to go beyond that. Less than or equal to so we can find some n at which it goes beyond it. and this is less than equal to omega, and omega is less than equal to what we get. So kind of this represents the probability we get from P omega if we cut it off and then continue with zeros. This is what we get from P omega itself, and here I'm going to write what happens if we cut P omega off at n and then continue with all ones, and that's the same formula we've got here. Plus 2 to the minus n. Now, there's a strict inequality between these two, so something here needs to be strict. Okay? In fact, one can prove that omega is irrational, and that means that both these are strict. But we're not going to need that fact. I mean, we're not going to need the fact that these inequalities are strict, although I've got that written down in the notes. What troubles me a little bit, I mean, it's not a real trouble because, so in the notes I just state that omega is irrational and I don't prove it. And I was wondering if the proof goes through without that assumption. But I kind of have a feeling now that the fact that omega is irrational is needed to know that this n here, that we find an n such that this inequality holds, because otherwise it could potentially be the case that you know, if this is going up to an irrational number, eventually it's going to is guaranteed to get past this number. Otherwise, you can imagine that the sum to infinity would be this from anyway. So everything works with the assumption that omega is rational, or with the fact that omega is rational, that's not proved in the notes. In which case we can put strict inequalities here. That gives more information, but it's not needed. Anyway, we have that, and so this will sum out. Okay, so now we look at, here we've got omega sandwiched between these 2 points. Or in fact, we've got these 2 values sandwiched here. So if we consider the difference of this 2, then it's smaller than the difference, then it's less than or equal to the difference of this 2. So we have that omega minus the sum, minus the sum of the weights of these cylinders, the first n parts of the domain of the universal function. So this is less than or equal to less than or equal to the difference between these 2, which is 2 to the minus n. So in the notes I have this strict inequality here. Maybe let's just accept that omega is irrational. I wish I just. So let's make these strict and then we put the strict inequality here. Because then the next thing certainly holds. So I say always, anyway, just reading through this before the lecture, I got the idea that maybe because I don't prove it's irrational, maybe I could actually get away without that. But I've got so many doubts about it, and it just seems better to use the language than as irrational. Anyway, so omega minus this is less than 2 to the minus n, which that means if we look at what's left, and I'm not going to move the camera, but looking at the formula for omega as the sum over all the cylinders in the domain of their weights, then the remaining cylinders that we haven't included up to the first n, capital N cylinders that we're looking at, the remaining cylinders clearly add up to, to this difference here, and that's less than 2 to the minus n, which means every word that's in the domain of, that's in the remaining domain of omega, of the universal function that we haven't included so far, has to contribute a weight strictly less than this, which means all words are all such words have length greater than n, than capital than little n. So we have every wi that's in the domain, so that's a word in the domain of the universal function, whose where I for I greater than n, so one capital N, so one that we haven't considered before, is such that wi, the length of wi, is greater than little n, because its weight needs to be strictly smaller than 2 into minus n. So for every, now we get a really crucial observation, which is quite straightforward, that every finite word v that's not in the set of words we get by applying universal function to the words 0 to the first n elements, capital N elements of the domain of the universal function, every such word v here, if it's obtained as u of something, so every such v will arise as u of something, and its prefix-free complexity is the length of the smallest sequence w such that v is u of w. Sorry, this is for every v not in this set, then the smallest w in the domain of the universal function such that v is u of w, well, it's obviously some wi that's outside these, and therefore the index is greater than n, and therefore the length of it is greater than n. So in other words, for every v, the prefix-free complexity of v is greater than n. Naturally, we have the less than equals here, we have the greater than equals here, that would still be okay, because we can be off by 1. So actually, everything, well, never mind. Let's stick with. So in particular, f of p omega restricted to n is such a v, and it has, so f of p omega restricted to n is such a v by its definition, hence complexity of f of p omega restricted to n is greater than n, which is what we needed to show. Good. So, my apologies about the confusions with the strict and non-strict equalities. You can think to yourself, so the proof's written up nicely in the lecture notes, and in the lecture notes there's a lemma beforehand. Is this lemma or is it just a statement that it's not written down as lemma, but it's a statement that omega is irrational. And a good exercise, try and think for yourselves whether that irrationality is actually really needed in the proof. It's certainly needed in order to say these two inequalities are strict, but whether or not that's really needed, I'm not sure. The place that worries me a bit more is whether the irrationality is needed to show that there exists some n at which this sum will go beyond this one. Which clearly holds if omega is irrational, and as n tends to infinity, this is approximating an irrational number because this is a rational number. Right, good. So it's that was quite technical. You can see my mind's still a bit in the Christmas holidays or something. Are there any questions on that? Or anything else? Okay, good. So that's it for today, and see you next week.